Hello and welcome to, well, anyone who wants to watch my video. Today, we're going to be talking about graphs and putting labels on graphs. Another very exciting stuff. We're going to be taking a bunch of nodes and edges and putting labels on them so we know what things are. Now, why do we do this? Best way I can explain actually is with an example. Say we've got a factory that makes, I don't know, factory parts. And we've got various processes represented by each node, or could be machines, could be, various machines in a production line. And we've also got edges, which will represent the inputs and outputs. And from these two things, we can group the nodes and edges into categories. Say, one thing we might want to look for instance, is machines that are operating at a high capacity. Or we may want to be estimating what sort of time each of these processes might be taking, and we can do that by looking at various parameters within the nodes and edges themselves. Now, this can also be applied to deep learning neural networks. That's right, we actually are making neural networks of neural networks. I mean, surely when you started studying AI, you knew that would happen at some point. But it's a number of reasons this could actually be very helpful. Could be helpful in analyzing our networks and figuring out how they're working and what's going on. It could be useful in optimizing them. Say you've got say you're looking at certain inputs. If you've got combinations of certain inputs, say you've got like a high value from a soft plus function and a low value from a ReLU function, and that may inform what sort of parameters that you want to set in the neuron that goes into what sort of what sort of optimization, what sort of activation function, and things like that. The other thing that I could see that it would definitely help with is picking up on errors, because if you get a final output with pretty low accuracy, or just an output that you weren't expecting, you classifying the neurons and edges within the network might help you identify anomalies that you could look at, either neurons or groups of neurons that aren't behaving like regular ones, and see if you can figure out patterns on what might be causing those outputs to be not what you're expecting. Now, the paper that I am discussing today is called, so I can find it, Neural Structured Prediction for Inductive Node Classification. Now, basically what this means, originally, the way we would label graphs and nodes, and still to this day, there's a lot of graphs that do that, and there's a lot, it doesn't matter that much, because a lot of graphs are pretty simple, like the ones that we do with our training algorithms. We have the same, we put in all our parameters by layer, and we have like 2 to 3 layers for each one, so there's really no need for a complex labeling algorithm. But originally what would happen is that like a small number of edges and neurons would be labeled, and then they would just assume the labels for the rest of the graph based on that small amount. So you got like 1% of the graph just informing and guessing the other 99% of it. Now, that was pretty much the only way to do that until graph neural networks came in. Now, what a graph neural network is, that is what's like a machine learning algorithm. It operates on marginal probabilities. That's looking at the probability of various values for each cell, for each neuron, or for each edge. It'll look at the probability that it could equal 1, the probability that it could equal 2 or 3, or so on, whatever the subset of potential values for potential classifications for that is, and obviously it'll go with the one with the highest probability. And that's why it's called inductive, because it will start with this small key number of neurons and work outwards on marginal probability. The one issue with graph neural networks is that they don't take joint probability distribution into account. They assume that each neuron and each edge is completely independent of everything else that connects to it, which obviously is overlooking a whole lot of potential information which could inform your labeling and improve the accuracy by quite a bit. So one of the things that the authors of the paper have done, if I can find the paper, I'll tell you. Okay, yeah, one of the things the authors of the paper have done, Ming Qiu, Jen Tang, and Huan Kai, I think. What they have done is they have added joint probability distributions, which instead of looking at just the marginal probabilities of one label for a cell or an edge, they look at combinations. They look at the marginal probabilities that there'll be a cell of a certain value with an edge of a certain value next to it. So it's basically just more work intensive, more computationally intensive. But they also incorporate another aspect into these as well. They incorporate something called, what do they incorporate? They incorporate something called conditional random fields. Now, what this is basically it's an optimization function, and you'll have a function, and you'll have weights generated by certain values within, or certain parameters within the neural network. And now what the authors of the paper do, they generate the parameters by running GNNs. They run two GNNs. They run a GNN for the nodes and a GNN for the edges, and they generate obviously a bunch of probabilities, probable labels for each one, and they use that to parameterize the optimization function, and they're able to get pretty high accuracy by doing this. Now they test this obviously by running an experiment. They run an experiment with the PPI data set, which is basically a set of 20 training graphs. To make it a bit more challenging, they try using only the first one, the first two, and the first 10 training graphs, which they put into a different another 3 data sets and train them on all these. And they compared this with pure graph neural networks and also pure random fields, and each time their optimization function, which is known as a SPN optimization function, each time every time actually this function was the superior accuracy. A lot of them with the when they used all 20 graphs, their functions got up to 99.41% accuracy. That's compared to things like there's a lot of 98s and 86s and whatever, but the SPNs do have are up in the 99s. They do have a high degree of accuracy, which can actually mean, I'm sure you probably know by now, can actually mean quite a lot in machine learning. It can be very difficult to get up those couple of percentages. But basically they figure out their SPN model, which uses, like I said, it uses 2 graph neural networks, which generate probabilities for the nodes and edges, and then they use that to populate to parameterize an optimization function that works with conditional probabilities, and use that to get a pretty impressive level of accuracy. Let's see if there's anything. Oh, the other thing that they do once they've run this optimization function, they also refine the joint distribution by solving the maximum gain. Preferred relations can lead to formal improvements. So the maximum gain is like it's looking at so maximum gain is basically tuning the parameters and the values in the optimization problem, in the function in the optimization problem, to try and maximize the probabilities of the values that are predicted. So we try and get predicted values that have the highest possible probabilities. And yes, I did just pause the video to look that up. But that is about, like I said, in conclusion, that's the... I also want to talk about, obviously, how this relates to what we've studied so far. Well, it's basically just building another thing we can build onto deep neural networks, and a way we can improve our optimization and our handling of errors on these networks. Looking at probabilistic distributions, that's also something we could potentially be building networks that use probability, rather than just plain classifiers. It obviously also ties in with stuff we've been doing because of the experiment that they ran. They're running a deep learning experiment that uses, well, it doesn't use a neural network, but it does. It gets parameters from the neural network and uses that to guess the labels on it. So in a way, that does build on what we've learned. And yeah, let's just have a look at, just clarify what exactly they conclude from this. Find their conclusion. Okay. Paper, they studied the inductive node classification. They proposed the SPN method, which I reiterate was you taking two graph neural networks, one of the nodes, one of the edges, and using the probabilities from that to parameterize an optimization function in a random field. And once they've done this, then they optimize the function itself, not the parameters, but the actual construction of the function, by looking for the maximum gain, which basically, like so many things in machine learning, is just they just run that on the computer and get it to do trial and error and find the maximum, find the maximum probabilities, like you would when you're doing a grid search. In future, we plan to explore more advanced GNNs model to model the pseudo-marginals on the edges, which are keys to improving node classification results in SPN. So yeah, basically they developed the SPN model, and it solved the problem of including joint probabilities and joint probability distributions rather than just marginals, and it gave results that were more accurate than plain graph neural networks or random fields. Okay, thanks for watching my video on neural structured prediction for inductive node classification. See you next time.